review guide without giving away the answers to the midterm review guide. We'll see how that works out. Several of these are kind of obvious. Anyway, so the first 1, 2, 3 questions, 4 questions are all about physical and chemical. And so we need to talk about physical and chemical and indicators of a chemical reaction and physical versus chemical properties. So I want to talk about properties first, even though both of them are similarly linked. So when we talk about properties, physical versus chemical properties, whenever you talk about a chemical property or a chemical reaction, there has to be a rearrangement of the atoms. Like hydrogen plus oxygen goes to water, right? And then we need 2 of these and 2 of these. So there has to be a chemical rearrangement, a rearrangement of the atoms. Instead of just hydrogen and oxygen, now I have water. And so that's what you're thinking about when you're looking at a question of physical versus chemical properties. So on this worksheet that we did before, this is going to be a kind of a good tester for me to go down, and then you can look at the worksheet, the review, and determine if you agree with me. And we're talking about physical properties versus chemical properties. So in order for the property to be tested chemically, there has to be a rearrangement of atoms. So let's talk about blue color. So if an element is blue, is there a rearrangement that I have to? No, there's no rearrangement of atoms to test that. I can look at it and see that it's blue. Same with density. Density, all I need is a mass and a volume, right? Flammability. Combustion is definitely a chemical reaction, right? It's one of the 5 types that we've talked about already. So flammability is definitely a chemical property because in order to test it, I have to have a rearrangement of atoms. Solubility. So solubility, we're just talking about dissolving something in a liquid. It definitely doesn't require a rearrangement. If I dissolve sugar into tea, I can get the sugar back out by evaporating off the water. I'll have the tea and the sugar mixed in the bottom. So solubility, physical property. Reacts with acid. When you see that word, reacts, you should automatically just know that it's a chemical property because a reaction is definitely a rearrangement of the atoms, right? Right. Supports combustion. Well, again, combustion is a necessary, we have a hydrocarbon CH, and we're just going to make a generic hydrocarbon plus oxygen goes to CO2 plus H2O. We know that is combustion. We know that there is a rearrangement. So supports combustion is definitely going to be chemical property. Sour taste. I can taste this piece of paper. I'm not going to, but I can taste this piece of paper and there's no rearrangement of atoms. Melting point. If I melt an ice cube, it is still water. It was water in the ice cube. It's water once it melts, so that is a physical property. Reacts. Whenever you see that word, then you know that is a chemical property. Reacts with water, reacts with a base, reacts with acid, reacts with oxygen, reacts with something. If it reacts, that is a chemical property. Hardness. Well, I can test this for hardness, and there's no rearrangement of atoms, so that's physical. Boiling point, I can boil water, it's still water. Can neutralize a base. Okay, if you're neutralizing a base, that is a chemical property. There's a rearrangement of atoms. It is making water and a salt, which you will learn in acids and bases later. But it takes an acid to neutralize a base, and there is definitely a rearrangement there. Luster, how shiny something is. This pen is shiny. I don't need a rearrangement of atoms to tell me that. And odor. An odor is definitely a physical property because I can smell this piece of paper without rearranging the atoms of it. So that's physical versus chemical properties. Now I want to talk about indicators of a reaction because that's really what you're talking about. You're talking about physical versus chemical properties or an indicator of a reaction. So let's talk about indicators of reaction. And what are they? The big two that we've talked about before are a precipitant. And we all know that that's a solid that forms from two solutions. Right? So I mix two liquids together, or what appear to be liquids, and I get a precipitant, a solid. You saw it in the bottom of a test tube, hopefully, when we did our lab, where we precipitated out a yellow lead sulfate, I think it was, or lead nitrate. Anyway, a precipitant, a solid will form. And if we spun that test tube down, we would have gotten the solid at the bottom. But anytime you mix two liquids together, you get a solid. It looks like it's snowing inside, or they say a solid is formed, or you see a solid, then you know that that's a precipitant. That's an indicator of a chemical reaction. Next one is bubbling. And notice I said bubbling, not boiling, because boiling is a phase change. Bubbling is the production of a gas. You saw it when you mixed magnesium with hydrochloric acid. When you did metals, nonmetals lab. Hopefully you've already done that. Bubbling, production of a gas. That's what happens when we put magnesium into an acid. And then we have a temp change. We have a permanent color change, like rust. Permanent. Did I spell permanent wrong? No, of course not. I didn't spell permanent. Color change. And then we have an odor. An odor would be the least strong evidence, like it would be very weak evidence that something has changed. Because what if some odor wafted in while you were seeing if this chemical reaction occurred? It could happen. It's not our best. It's not our best indicator. And then I've got two more. Gives off light and produces water. We didn't really talk about produces water much. I showed you in the when I did the whoosh jar that it formed water from combustion. So I did show you that production of water. There was a temp change with that, and it gave off light as well. Some people will tell you that it can't give off light without a temp change, and I will refer them to glow sticks. Or there are some other reactions that might be exothermic or endothermic. They might produce heat or take in heat, but on such a small scale that it would be hard to notice just as an indicator of a reaction unless you had a thermometer in there. So these are the big ones. These are what you want to look at. If you look at it with an eye thinking, okay, was there a rearrangement of atoms? Did I see any of these indicators? But anyway, you can go through 1, 2, 3, 4. You can go through 4. Oh, by the way, strike through sodium and make that potassium. We're not talking about sodium. We're talking about potassium. This whole thing talks about potassium, and then all of a sudden we go to sodium. I don't know why. But anyway, you can answer 1, 2, 3, 1, 2, and 3 to here. So the whole first page, front and back, is basically physical versus chemical. And this one question here, where they're discussing this crime scene powder, and they want you to look at it and compare it to all these other powders, and then they're reacting it with some things or making some observations about its physical properties. And you can just go down the list and compare your crime scene powder to everything and eliminate ones that don't fit the crime scene. Turns red. No. Absorbs water. No. Like, you can tell what it is, okay? All you have to do is use the process of elimination. Just go down the list, decide if the crime scene powder is like one of these 5 things, okay? So that's the first sheet. And now let's take a look at the second sheet. Oh, wait a minute. We didn't get to the bottom of the first sheet. Yeah, we did. Okay, so it's another justify a chemical reaction has occurred. So you have to see what observations they've made and justify based on their observations and your evidence that a reaction has occurred, and decide what's the strongest evidence that a reaction occurred in this case. Okay. Same with number 4. And then finally we get to number 5 and we get to a density problem. And it looks like they've given us the masses of 3 things and the volume of 3 things. And then if I turn this sheet over, it looks like they want us to put them in order from top to bottom. They want us to put them in order from top to bottom. So really, the real question here is 2 things. One, can you calculate density? And 2, do you know which things end up in what order? So I'm gonna do an example of a density problem. Somewhere I have a density problem. What have I done with my density problems? No, that's not it. Okay. Okay. Somewhere around here, I put a density problem. Some density problems. And now I don't know what I've done with them. Okay. All right. Well, I'm going to make up some density problems. So, if I have something, let's say I have element X, Y, and Z, and we have masses of 28 grams, 10 grams, and 8 grams. And we have volumes of 20 milliliters, 18 milliliters, and 16 milliliters. Then we can calculate the density of these things. Basically, of course, my least professional video yet. We can calculate the density of these things. Now remember, on the back of the periodic table is the density formula. Density equals mass over volume, right? Or if you have gotten used to the triangle, you know what's on top, because what's on top, right? Okay, so I have masses and volumes, 28 divided by 20, enter, 1.4 grams per milliliter. So this is a volume and a density. And then 10 divided by 18 is 0.55 grams per milliliter. And then 8 divided by 16 is 0.5 grams per milliliter. And so they're asking what order these would appear in a container. And we've done a density column before. So we've done a density column before, and we know that the most dense things end up at the bottom, and the least dense things end up at the top. So we just have to compare these densities. Well, we have 1.4 grams per milliliter, 0.55 grams per milliliter, and 0.5 grams per milliliter. Well, the most dense thing, the thing that weighs the most per unit of volume, is 1.4 grams per milliliter. So element X is at the bottom. And then we have elements Y and Z. So let's decide where these two will end up. So element Y at 0.55 grams per milliliter is obviously going to end up in the middle, because this is the least dense, 0.5 grams per milliliter. Element Z is going to end up at the top. So if I did a density column for this imaginary elements X, Y, and Z, this is the order they would take on in that density column. I hope that helps with the question at hand. Yeah. Yep. So question 5, yep, you've got 3. Yep, you're just going to have to do some densities. You're going to calculate some densities, and then you're going to say where those 3 things end up, where those 3 things end up in a column. And the next question is just asking you the same deal. They're giving you 2 things. They're saying that bromine gas is less dense than air. Bromine gas is less dense than air. And what will it end up looking like? Well, if bromine gas is less dense than air, you know the densest stuff is going to stay on bottom. The less dense stuff is going to be on top. You can figure out which of these is going to happen. We're not going to assume that our gases are mixing at all. So it's going to be Q or S. We have to assume that that it's something that we can actually separate. Okay. So, no. I'm sorry. I've read the question wrong. They said that bromine is less dense than gas on this side. Which of these 4 jars would it look like if after 4 hours, if air were more dense than bromine? So you're still looking at Q or S, but you're just saying if air were more dense than bromine. That's the same answer. Bromine gas, which is less dense than air. Bromine, air. And then they're saying if air were more dense than bromine, which means that bromine gas is less dense than air. So Q or S? It's one of those 2. We really need to take a look at this review. Anyway, we'll continue on. Density problems. Density. We've already done something like that. You know what the formula is. It's on the back of your, will you have it? Because you won't have the periodic table. You'll have their periodic table. The electronic version, I'm going to assume that they have to give you that. If it's on the back of our periodic table, it's probably going to be on their periodic table too. So most of you by now have learned this one simple formula. So you know that that's all you're doing. You're plugging in the things you have and then calculate. So that's going to get you 7, 8, 9, and 10. All right. So let's see where we're at here. God, this thing's a mess. Prime steam powder. Yep. Okay. So we got that. We got density. Okay. And then we have balancing. Balancing equations and reaction types. Let's look at balancing. You've probably already, let me grab some balancing practice from somewhere around here. Oh, balancing practice. There's balancing practice. I don't know, somewhere. Aha, I found it. Okay, here we go. Balancing practice. So the idea here is that everything has to obey everything has to obey the law of conservation of mass, which means that we can't create or destroy matter, which means that both sides of every chemical reaction have to have the same numbers of atoms of the same types. If not, then you would have a different mass on one side to the other. So the way I do it, and I'll show you, and then you make a decision for yourself. So there's 2 ways that I balance reactions. One, I either do atom counts, N and O, and then I count the number of atoms on the left side. There's 2 nitrogens and 2 oxygens in here, right? I'm going to move this camera up a little bit. And I have 2 nitrogens and 5 oxygens on this side. So I know that I need to make this side match this side in number of atoms. And I also know that I can never get a 2 to multiply times anything to make it 5, or even an odd number, so I need that to be even. The quickest way to make an even number is to multiply it times 2. And now I have something I can solve. And now it's just, what do you want to fix first? If you want to fix nitrogens, I have 2 here and 4 here, so I know I need to put a 2 out here. That gives me 4, and I have 2 here and 10 here, so I know that I put a 5 out here. That 5 multiplies times that 2 gives me 10 oxygens. That 2 times 2 gives me 4 nitrogens. On this side, that 2 times 2 gives me 4 nitrogens. That 2 times 5 gives me 10 oxygens. Now I know that I balance on both sides. That is a balanced equation. Or the other way you can balance it is if you can balance it in your head. And that's, it's harder. Some people are just intuitive that way. Like I see that I have 8 sulfurs here and 1 here. I know that I'm going to do 8 here. That's going to give me 8 sulfurs and 16 oxygens. I know that I need to get 16 oxygens out of this. I put an 8 right here. I'm done. That's balanced. That's 8 sulfurs, 16 oxygens, 8 sulfurs. 8 times 2 is 16 oxygens. And that's it. So those are the 2 ways to balance an equation. You're just playing with the numbers, remembering that coefficients must multiply times subscripts, remembering that it stops at the plus sign or at the arrow. It doesn't keep multiplying through everything throughout the problem. And then we got to talk about types. So the way I recognize reaction types, if you have one product, then that is definitely a synthesis. If you have one reactant, then you know that is decomposition. Okay, and then we just get down to the other 3 reaction types. And so we have single replacement, double replacement, and combustion. So the way I know double replacement is I have 1, 2 elements, 1, 2 elements, 1, 2 elements, 1, 2 elements, and they trade partners. So vanadium is no longer with oxygen when it's on this side. Vanadium is now with sulfur. Calcium is no longer with sulfur on this side. Calcium is now with oxygen. That is a double replacement. Now, if I go down here, I see single elements on each side, and it's a different element on each side. So one thing has swapped places. So I have this sulfate hydrogen here, right? And then on the other side, aluminum's with it, and hydrogen is by itself. So that is a single replacement because one swap has taken place. Hydrogen is swapped for aluminum. That's one swap. Here, vanadium and calcium have both swapped partners. That's 2 swaps. And then the last type of reaction here at the bottom, again, the generic form is a hydrocarbon plus O2 goes to CO2 and water. Whenever you see O2 as a reactant, CO2 and water are your only products, you know that is combustion. And that's my quick rundown on balancing and types. So hopefully that'll get you through. Let's see. 11, 12, 13, 14. What type of reaction occurs when 2 or more simple substances combine to form one more complex substance? So the key here is one more, and that's a product. So basically one product. If it forms one product, we just talked about it. What is it? All right, so you should be able to get down through here. So hard. Okay. Average atomic mass. Now I know I have that worksheet somewhere around here. Let me find that thing. Average atomic mass somewhere. No? Is it not here? Aha. Okay. Average atomic mass. Okay, I'm gonna have to change the percentages on this one just a little bit to make it right. But basically, there's a way to calculate average atomic mass. I'm gonna go through the necessary skills on how to do this. It's a process, right? But I'm gonna change some things. I'm gonna make this 70% and this 30%. I'm just gonna make it 70 and 30 so that it adds up to 100%. Unlike what it was. And then we're going to talk about how to do this. Well, it's steps. It's a process. So step 1, convert percent to decimal. Now there's 2 ways to do that. You can either divide the percentage by 100.7, or you can move the decimal place 2 places. So if I move this decimal place 2 places, it becomes 0.7. If I move it 2 places here, it becomes 0.3. Step 2, multiply mass times converted percent. So I've got a mass here, 23.985, and I'm going to multiply it times my decimal, times 0.7. 23.985 times 0.7 gives me 16.7895. Now there's another mass and another percentage. Well, guess what? You do it for how many ever you have. If you have 3 isotopes, then you do it for all 3. If you have 5 isotopes, then do it for all 5. If you have 20 isotopes, do it for all 20. Okay, 24.986 times 0.3. That gives me 7.4958. And then the last step, step 3, add answers. So 7.4958 plus 16.7895 equals 24.2853. That's my answer. Now, I'm going to add a step 4. That's the process for determining the average mass. But I'm going to add step 4, and step 4 is going to be check your answer. Your answer should fit in between those 2 masses. If it doesn't fit between 23,985 and 24,986,
Mr. Perez, please dial extension 344-7616.
Lovely interruptions. Then it is not a good answer. 24.2853 fits right in between those. It's closer to 24, which is magnesium 24, which is the most abundant. It has the highest effect on the average atomic mass, so that is a true story. So that is how you calculate average atomic mass. The next 2 questions are exactly that. Remember, step 1, convert percent to decimal, multiply times your mass, and if they give you a mass number instead of an exact mass, that doesn't matter. We can use that mass number. 35 times my converted percent, 36 times my converted percent, add my answers. Does it fall in between 35 and 36? That's, and now they're asking greatest effect. Well, I can tell you, whatever has the most abundance has the greatest effect. Whatever has the least abundance has the least effect. So I'm giving away 2 answers there, but there's not much in it other than because I need you to know that. Okay. Isotopes of hypothetical, the average atomic mass of this is which isotope is most abundant? Well, you know that whatever you round your average atomic mass to is going to be your most abundant isotope. So 62.831, what does it round to? You better know your rounding rules. Remember, you need to look, watch, make sure that you don't round like 5.890 to 5. That doesn't round to 5. That rounds to 6, right? So make sure your rounding is correct. Okay, that's sheet number 3. Sheet number 4, another abundance question. You know how to answer that. Which of the student statements is true regarding abundances? We've already talked about abundances and isotopes of chlorine. I'm going to hope that you know how to answer that. And then determine the best way to identify the unknown substance. Okay, so what do we know about identifying an atom? What is the identifying subatomic particle? Well, it's protons, right? We know it's protons. So really, that's the instant thing I'm going to start looking at instead of color. A lot of things are yellow. A lot of things are solid. Most of the periodic table is solid at room temperature. So that doesn't help me much. But what I do know is that if you give me the number of protons of something, that I can determine what it is on the periodic table, right? Right. Okay, again, basically a very similar question. They're asking us to look at these nucleuses and compare them. And what do we know? Well, without looking at those nucleuses at all, what I know is if it has the same number of protons but a different number of neutrons, it's an isotope. And if it has the same number of protons, that it is definitely the same element because that is the identifying particle of an element, correct? Yes. All right. So I'm going to let you figure that one out. Hopefully by now you should be able to figure that one out. Okay, let's talk about these guys. Let's talk about Rutherford, Thompson, Bohr, and the current atomic model. So we got to talk about each of their models first. So I'm going to draw each of their models first. So J.J. Thompson, he basically thought everything looked like a plum pudding, right? So that we had a positively charged media. That's really all he could figure out. And he figured out the size to charge ratio of electrons. And so he knew basically that we had some negative charges, we had some positive charges, and that's the pros of his model. Like he figured out that we had positives and negatives that and the size to charge of the electron. So that's the pros of his model, is he basically figured out what an electron was, or at least what it was charged. And then we got Rutherford. Rutherford was the guy that shot alpha particles through a piece of gold foil, and he figured out what? Well, he figured out that when it hits the middle, it reflects straight back at him, but that's super rare. Why? Because an atom is mostly big, empty space, right? So what he did figure out is that the nucleus of an atom is a densely packed, positively charged nucleus. That's what he figured out. That's what his model tells us. The pros of his model were that he told us that we had a densely packed, positively charged nucleus, and that an atom was mostly empty space. He told us that an atom was mostly empty space. He didn't figure out where those electrons were. But along came Bohr. Bohr figured it out. He figured out where electrons were. He figured out that electrons hide in these shells, or energy levels. You can call it either thing. I prefer energy levels, also known as periods down the periodic table. But he figured out where electrons were. He figured out that they hung out in shells. He also figured out that they could jump energy levels and that when they fall back down, they emit light. And then we got Erwin Schrödinger, man after my own name, who did electron distribution based on probability. The pros were that he indicated exactly where the electrons were. Erwin Schrödinger figured out that with a big messy math problem that we could figure out where exactly each one of these electrons was going to hang out. Hopefully you can figure out the cons of each model. There aren't a whole lot of cons with the current atomic model unless you get down onto a quantum scale, which we're not going to talk about. So anyway, that's me doing the review without actually doing the review. It's kind of awkward. I know it was kind of awkward for me. Some of these questions, there's no way to tap dance around the knowledge without tap dancing around the answer. But that's it.